Okay, so pick up right where we left off last time. We were working on this, the flux through this closed surface that was formed by the cone and the top disk. And so we said S1, we were going to use R and theta, right? And so we said R1 was R cos theta, R sine theta, and then Z was the same as R, is that right? And then for S2, R2 was R cos theta, R sine theta, and 4. Okay, so we'll do the flux for S1 first. So S1, so we're going to have to do the cross product. So for S1, what do we want? We want the F dot R cross R theta dr d theta, right? Okay, so the common question that comes up is when you're is it r dr d theta or just dr d theta, right? This is a common question. If you parameterize your surface in terms of r and theta, then you're just going to have dr d theta, right? So dA will always be, for these problems, du dv. Nothing else, just du dv, okay? And then what happens is, when would you substitute? So if you work through a problem and say it's in rectangular coordinates, and you work it out, and then it's, say, dx dz. So that's your dA in the problem. And now, so now you have a standard double integral. It's no longer a flux integral, it's just a standard double integral. And you want to switch this to polar, then you're going to do r dr d theta. But when you start off parameterizing your surface in terms of r and theta or phi and theta, you'll always you will not stick that thing in there, because actually what will happen is that will happen in the cross product. So you're not going to have the r here, you're not going to have rho squared sine phi, that stuff. You'll just always just do dr d theta, whatever, this is the dA. Okay, does that make sense? So the only time you would actually inject the r dr d theta, is if you have a standard double integral in rectangular coordinates and you're going to change it into polar. Then it's r dr d theta. But if you start by parameterizing an r and theta, then it's just dr d theta. Okay, so let's do the cross product question. Yeah.
So with that, like, that would be, for instance, if you had like xyz, two xyz vectors, f and r, and you did the cross product for r first before converting it, then you would need to include an r, right? Like if you were, so if you did your cross product.
So you do this whole thing in terms of x and z. And then in the end, you have something blah, 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 dx dz. Now we say, oh, now I want to change it. Right. Then you need to, okay. That's right. Because you have just a standard double integral in rectangular coordinates. Dx dz is equal to r dr d theta.
Right.
Right. But if you start off this way, then we're just going to have dr d theta. Okay, so, because this is the key in these surface integrals. dA is always going to simply be du dv. Right? U and v are the two variables we choose for parameterization of the surface. So nothing else, just du dv. Okay, so we're going to do, and then r sub r is going to be, what is it? Negative sine theta, negative r sine theta, and then r cosine theta, and then 1. And then with respect to theta, it'll be, did I do that wrong? That's wrong. Just cosine theta sine theta, sorry. I think that now, so now I want that's the one I want below here. Negative r sine theta, r cosine theta, and 0. Do I have the matrix set up right? For partial of r with respect to r, partial of r, r1 with respect to, yeah.
I just go, how do you know what order to put them in?
All right, we're just about to get there. About to get there. So yeah, that's a great question because theta is not a direction, right? And so you can't really use the right-hand rule with theta. So this is what you do. You just try it one way, and then we'll see what happens. So we get the vector out of this. We get what vector? We get the vector negative r cosine theta, r sine theta, and r?
Negative r sine theta.
Negative, negative, and then positive r?
Yeah.
Someone confirm that? Thank you. That's good. Saves time. Okay. So here's the key. So do we have it right? So what did we want? Outward orientation. So for this cone, what is outward orientation like? What are what can you say about every single vector for that cone if you have outward orientation? The z component is less than 0. So then we look at this. Is that what we have? No, we have the z component greater than 0. So this would be inward orientation. So if we were to flip these, do r theta cross r, then we'd have negative r, and that's what we want. So that's how you can tell. Look at your cross product and compare this, whatever sign applies to the orientation specified in the problem. So this is inward. And so to get outward, we should have done r theta cross rr. But that's as easy as changing the signs, right? So then outward would be r cosine theta, r sine theta, negative r.
So
and that's what we want. Absolutely, because we need that's cross product, just changing the order of a cross product, just takes the opposite vector, right? It's the opposite vector.
Oh, okay.
Because we're doing a cross product. Yep. Do you still have a question?
I thought you had something wrong, but you had it right.
Okay, cool. No, please tell. Yeah, don't hesitate. Even if you think and you're not sure, speak up because we don't want to dig a hole in these problems, as you're finding out, I'm sure. Okay, so we got that, and so now we're ready to set this up. F is y negative xz. So we're going to use our x, y, and z from S1. So it's going to be over the surface. F is y, so it'll be r sine theta. Negative x is negative r cosine theta. Z is r dot. Now we're going to use this one, right? We want the outward oriented one. R cosine theta, r sine theta, negative r, and then just simply dr d theta. Don't. So the r of r dr d theta is in this cross product. You see they all have an r in them? There's the r. That's the r. So that's why you don't put an r with the dr d theta. Okay, so the r is there, right there. So now we do the dot product, and we get r squared sine cosine minus r squared sine cosine. That's nice. Plus r squared, or minus? Minus r squared. And so then is that just minus r squared in the end?
Yeah.
And so then our r goes from, so this is the cone, r goes from 0 to 4. So it's the projection, right? So you take that surface, we got the double integral, you're going to project it into, well, no, you don't project it. You just, yeah, because it's r and theta, like in the xy plane, right? It's r and theta around the z-axis. So you're doing the polar, you're projecting it into the polar plane here. So 0 to 4. Before, yeah, so yeah, the circle would be x squared, yeah, so it is 4. And then 2 pi. Negative r squared, dr d theta. Okay, very good. And anyone have this? Man, thank you. What is it?
Negative 128 thirds pi.
Negative 128. That?
Yeah.
Okay. Very good. I am out of room. See if I can make myself some more room here. Maybe if I actually. No. Okay, so now we want to do. See if we can get S2 in there. So S2. All right, so S2 is going to be, we need the dot product, so it's going to be IJK. And then, so maybe we'll try, so because this R theta got us positive, so now we want Z to be positive, so maybe we'll try it the exact same way we did this one, and hopefully Z will be positive, but if it's not, we just change the signs. So we'll do same thing, cosine theta, sine theta, what, 0 now? Is that right? And negative R sine theta, R cosine theta, 0 again. Is that right? So now all we get is a K component. So this time we're going to get 0, comma, 0, comma, R cosine squared. Did I do it? Am I doing it right?
Yeah, plus R.
Which this equals 0, 0, R. And that, does that agree with outward orientation for this top disk? Positive R, outward orientation would be positive Z. So R is the Z coordinate. So we're just going to do that. And so then our integral will be R sine theta minus R, let's see, R sine theta minus R cosine theta. And Z this time is now 4. Dot 0, 0, R. dr d theta. Again, stop me if I make a mistake. Lots to keep track of here. Am I looking good? So we're going to do, it's going to be the same disk, right? This disk is the same as the projection of the cone into the polar plane. So it's still going to be 0 to 4, 0 to 2 pi. And we just get R, 4R. It's too much. And what is that? 64 pi? Which is how many thirds pi? 120. What's that?
192 thirds pi.
192 thirds pi minus 128. What is it? 64? And so why does this make sense? Well, because the positive Z component on our field, right? So that means that the vectors of the field are heading up, right? And so that we would expect outward flow through that cone to be negative. That's what we got. And then outward flow through the disk to be positive, because the Z coordinate has positive Z components for the field. So that makes sense that we got negative for the cone and positive for the disk. And so the total flux outward through that closed surface is 64 pi over 3, or the 64 pi minus 128 pi over 3. Questions on that? If you have a question, don't hesitate to ask. Oh, there you are. I'm like, I knew I saw you up there. Okay. Can I erase? Are we good? Okay. So let's talk about something called flux density. So flux density is like flux per, like flux through a closed surface per the volume that's enclosed. So that's how it's density, right? Per volume. So it's the rate of change of flow of vector field. It's the rate of change of flow. So that's why we do the flux of the surface divided by volume. And so if we think about it at a point P, again, make sure your listening is paramount to copying. All right. So it's going to be the flux. So the flux density at a point is going to be the flux through the closed surface around the point divided by the volume. Okay, so that's the general idea for flux density. Flux out through the surface and then divided by the volume, and then we're going to take that volume and take the limit as it goes to 0. So we're going to squeeze in around that point, and we're going to look at what happens to this ratio of the flux out of this closed surface relative to the volume inside. So then mathematically, that would be our flux integral, right, for the closed surface divided by the volume inside S. And then to get the flux density at the point, we let that volume shrink to 0 and see what this ratio does. See what this ratio does as you shrink down to the point. Okay, does that idea make sense? So that's flux density. Yeah, please.
So does it not just happen that it goes to infinity if the denominator is going to 0?
But your surface is getting infinitely small too. So it's like 0 over 0, right? Yeah. Okay, so here's a kind of a defining example. So consider the vector field xyz at the origin, and so we're going to consider the point of the origin, and that the surface is a sphere of radius a. Okay, so then what happens in this? So here's a little sphere of radius a. And then, so what? So at any point on that sphere, what is the vector? The vector is xyz. Well, do you see that vector xyz then at any point in the sphere would just be exactly the same as the radius vector to get to that point? Do you see that? Because they're the same direction and same magnitude, right? Because at xyz, then you'd have xyz. So then what's the magnitude of every vector on the sphere of radius a then? A, right? So the magnitude of that orange vector will be a. So the magnitude of xyz, if it's a vector on the sphere of radius a, then is a. So in terms of magnitude, that's really for all points on the sphere. That's constant. It's a constant field, right? It's a constant field. The direction changes, but all those vectors for any sphere of radius a are going to have magnitude a. All right, so we're going to recall that flux is what? F dot S. So it's F dot S. That was our main formula. And so we can use so we know that the idea of flux is that we're taking the magnitude of the force in as much as it's orthogonal to the surface, right? And that's our area vector, right? Our area vector is orthogonal to the surface and has area of the surface. So if you take as much of F in the direction of S, you get flux, right? And so that's what this exactly what this shows. Right? We do F cosine theta times the magnitude of S. So what would that be here? So what is the magnitude of F at all points on the sphere? A. And then what is S then? Surface area of the sphere, right? And then what is theta?
0.
Yeah, isn't it? So all these orange vectors are orthogonal to the surface already. So the theta is 0. So what we really just get is we get F is A, S is the surface area of the sphere, theta is 0, so the flux is just 4 pi A cubed out that sphere. So we don't have to integrate because we have constant force, and we can just use just calculate it for the whole sphere at once. So this whole surface area of the sphere is that's our S, and every vector has magnitude A. Is that good? So that's the flux. So what is the flux density then? So the flux density would be that flux divided by the volume inside the sphere, letting that volume go to 0. So we're going to take the 4 pi A cubed divided by the volume of a sphere, 4/3 pi A cubed. And what do we get? We just get 3. We get the number 3. So it doesn't matter what the area is, or it doesn't matter what the radius is. So it could be a large sphere, or it could be a really, really small sphere. So as you shrink the size of the sphere down to the point, it's still just the flux density just stays 3. Again, flux density is what? Flux divided by the volume inside, letting that volume shrink to 0. Well, in this case, it doesn't matter what the radius is. It's all that ratio is always 3. So any observations? Flux density is 3. At the point 0, 0, 0. That's right. So does the idea of flux density feel like anything we've talked about before? The rate of change of flow out from a given point. What's that? What's that? No, that was the divergence, right? So, check the divergence. What's the divergence of F? Partial with respect to x plus partial with respect to y plus partial with respect to z. What do you get? You get 3. See that? So flux density is kind of another perspective of divergence. It's really the same thing as divergence. This is not a proof, okay? This is just one example. That's kind of a defining example for how it works. On the next, I'll show the outline of the proof on the next slide. Yeah?
Does it work for all cases then?
Yeah, flux, that's what I'm saying. I'm telling you that it is true, but this is not the proof of it. I'm going to show you the proof on the next slide. Because we said what? Divergence was pointwise rate of change of the field in terms of expansion or contraction, right? And flux density is the rate of change of flow at a point. Okay, so that they're the same. So maybe I should say divergence is flux density, right? So we've talked about divergence before. Another way to characterize it is its flux density. Okay, can I go to the next screen? So here's just an outline of the proof. So you've got a solid E with a boundary S, and so that's the boundary of E would be a closed surface in the vector field F. Okay, so I'm just generically showing some solid E with boundary S. And we're going to look at, so that thing is all filled up with elements that are like boxes, right? So that thing's just like a whole bunch of boxes all filled in there. So we look at one box, okay? So here's one box, which is a little delta x by delta y by delta z. And suppose that, and we have the vector field F, so we have PQR at this certain point. So we have the point x naught, y naught, z naught. We have a typical box at that point. Dimensions delta x, delta y, and delta z. And then we have the vector at that point. So the volume of the box would be delta x times delta y times delta z, and that'd be delta v. Okay, so let's just look in the x direction. So in the x direction, you have what? The p component of the vector field. Well, that's what we care about in terms of expansion and contraction or flux density. And so then there's a little change in p associated with the change in delta x. So the change from the back of this little element to the front, you have a little bit of change in x, and so you're going to have a little bit of a change in this, the p component of f at that point. So the flux density is, so we're going to see the flux density at the point x naught, y naught, z naught, which is going to be the flux through the cube divided by the volume of the cube. And then let that thing shrink right down to 0. Okay, so this isn't bad, don't let it scare you. All right, so the flux through the cube is going to be, first of all, the sum of, in the 3 different directions. So we're just focusing on the x direction. So you're going to have what? You're going to have the change in p. What is flux? It's the vector times area, right? So it's going to be the change in p times the area of the face that it's orthogonal to, right? So that's going to be the change in p x naught plus delta x minus p, so it's this one minus this one, times the area, delta y, delta z. And that'll be the flux in the x direction. And you have a similar, some flux in the y direction and flux in the z direction. And that will all be over the volume of the little cube. All right, and so then when you split this up, you're going to split it up into 3 fractions. What's going to happen? So in the first fraction, your delta y, delta z is going to go away. So you're going to have the change in p for a change in x. And then in the second one, the delta x and delta z is going to go away. You're going to have the change in q for a change in y, etc. And so you see that that's our formula for divergence. So when you set up the flux density equation, considering all 3 sides of the little cube, and you work out the math, you get the divergence formula. So the flux density is the divergence. So this is just an outline of the proof. So if that's true, if flux density is the divergence, and flux density is flux over volume, then we can just change that around, and I can write that the flux is the divergence times volume. See that? Because if divergence is flux over volume, or flux density, then the flux out of one box is divergence times volume. Do you see that? I'll write this here. Let me do that. So the divergence of F is the same as the flux density, which is flux per volume, right? The limit, right? As v goes to 0. So so divergence is this ratio. Then I could just solve that for flux. Flux would be divergence times volume for a very small volume, right? For a very small volume. So that's what I'm writing here. I'm going to use this on the next screen. Okay, questions on this little outline of the proof? Yeah.
I forgot properties of limits, but can you just get rid of the limit and just say that equals that?
Because we're talking about I'm assuming a really small, super small volume.
Oh.
Yeah. So for a not small volume, no. But I'm talking now I kind of have taken the limit. Yeah. Because that's what divergence implies anyway, right? Divergence applies point-wise flux density. So yes. Okay, so this leads us to what's called the divergence theorem. Okay, the divergence theorem. So we're going to sum up all the flux out of all the element boxes, right? So you got like a three-dimensional. We got this solid. It's comprised of all these three-dimensional boxes. We're gonna, if we took the flux, we're going to sum up all the flux through all those boxes. Okay, and so we said that flux could be written as divergence times delta V. Remember that? So that's from the previous page. So you take that divergence times the little volume, that's flux. So I'm summing up the flux for all of those. But that's also what? You can think of those as surface integrals. So I can individually do the flux out of every box this way. But each of those fluxes is surface integrals. And so I've got all these boxes butted up against each other. And I'm going to do the surface integrals of all of them and add them all the surface integrals up. And they're all jammed against one another. What's going to happen? Right. So all the faces are going to be shared by two elements, right? Every face inside the solid is going to be shared by two elements, which are going to have equal and opposite flux. So when I sum up all those surface integrals for all those boxes, all the shared sides cancel out, leaving what? Right. It's going to be what? The surface integral of S. It's just going to leave the outside. So you have this, we saw this before with Green's theorem, that you have, when you have them all next to each other, you have this canceling effect. In this case, the flux for this side on this element is going to be equal and opposite to the flux of that left side of that element. Cancels out. So all that's left then are the ones that don't share a side, which comprises S. So therefore, these are equal, right? So looking at the sum of the flux as divergence F times the little point volume, summing them all that way, or taking the surface integral of the whole outside of E, they're going to be equal. All right, and so what does it mean to sum those all up? Well, you're going to be doing a triple integral, right? You're doing an integral in three dimensions of the divergence of F dV. So here's the divergence theorem. If E is a solid with a piecewise smooth boundary S, if F is a smooth vector field defined everywhere in E and on S, then what? These two things are the same. Two different ways to calculate the same thing. You can accumulate the flux throughout the whole solid, from inside throughout the whole thing, by doing divergence of F times dV. Or you can take the surface integral of the outside of it, and those will be equivalent. Yeah?
So what do you mean by smooth?
Smooth means there's no kinks, like a curve with. That's not smooth. It's continuous, but it has a corner point. So it'd be the equivalent. So like surfaces that you can't have a wrinkle, right? Like you can't have a. Yeah. Okay. So. Any comments about this? Notice what this is. This is kind of like rate of change, right? And this is a way to evaluate this that concerns the boundary. What is the divergence theorem? What's that? Yeah, did you see that this is fitting? Remember when we talked about Green's theorem, how we broke down how it was like a fundamental theorem of calculus? And there was qualities to it, right? Qualities are that, so accumulating what, bits of change using the rate of change, right? And so in this case, it's bits of change throughout the whole interior of the solid is the same as looking at what kind of like the overall change, or the overall result of that at the boundary, right? So this is the third fundamental theorem we've seen in this course. We saw the fundamental theorem of line integrals, and then we saw Green's theorem, and now we have this one. And they all have this parallel structure and parallel idea that you're accumulating a quantity using the rate of change. And in this case, we're accumulating flux, right? We're accumulating the flux throughout using the rate of change. And that can be expressed or calculated in a different way by looking at the total net change on the boundary, right? It's like the net overall change on the boundary. Next week we'll have the fourth one. So next week we'll have number 4. But it's really important that you see that since it's a fundamental theorem, it has these qualities. They all have these parallel or the same qualities to them. Yeah.
So S has to be like a closed surface?
Yes, it has to be the whole boundary of E. Yeah, absolutely. Questions on that? Okay, so let's look at not that. Let's look at this problem. Look familiar? Super familiar, he said. Just half an hour ago, right? So what does it want? It wants us to find the flux through S, the closed surface that's part of the cone, and below is equals 4. We just saw it. And we did what? We did the surface integral. We did S1 and S2. And we calculated this. Any other way to do it now? Does it meet the criteria for the divergence theorem? Yeah. It's closed surface. So instead we can calculate triple integral. Did you ever think that you would say triple integral is easier? But the triple integral is now easier. All right, so we can do the triple integral. What's the divergence of f? 0 plus 0 plus z is 1. And what's dv going to be? So we can say dz dx dy or something nice. Okay, but then we look at that thing and we say, what's that? Yeah, let's do cylindrical coordinates, which would be 1 times. So now we've got this rectangular and we want to change it to cylindrical. Will be r dz, still z, dr d theta. Cylindrical, right? Okay, and so then z goes from what to what? Z goes from what to what? 0 to 4.
0 to 4.
David.
It's square root of x.
The bottom is not 0, guys. The bottom is not 0. It's the bottom of the solid. Archer's down here, firing up. Yeah, this the cone, right? The cone is the bottom. 0 is not. The cone is the bottom of this. So Z is going to go from, and that's just R, right? Z equals R, 2, 4, and R is going to go from
0 to 4.
0 to 4, 0 to 2 pi. And what are we expecting for an answer? 64 thirds pi. Let's make sure here. So it's going to be do you just get, oh, you get 4 minus R, right? So you get, back to Z, 4R minus R squared. Check my math. So we get 2R squared minus 1/3 R cubed, 0 to 4. Does it work? Please work. So then that's going to be, is that 32 minus 64 thirds? Phew. Worked. Not that it shouldn't work, it just could have made an error in all the algebra. Okay, now, and actually there's, once we got to here, do you recognize that there's actually a third way to confirm this answer of 64 pi over 3? Yeah, because look what happened. Because our integrand turned out to be 1, this is the same as volume of the cone. Volume of a cone is 1/3 pi r squared h. There it is. Now, that only works, why does that work? Only because integrand is 1, right? Integrand is 1. Okay, this is especially handy with all the cube problems. So we saw like the cube that was sheared off last time, and then you had a cube problem in your homework. So doing the triple integral is usually much easier because a cube has 6 sides, right? So doing a single triple integral is going to be really helpful. There's one example, another example I want to show you here. Any questions on this? So again, what would it mean to verify the divergence theorem? It would mean what?
You just show it both ways.
You compute it both ways. That's what we did, right? We computed the surface integral earlier, and now we just computed the triple integral, show that they're equal. That's verify. Using the divergence theorem to find a surface integral would mean what?
Solving using the divergence theorem.
Which would mean, what are you doing then?
Doing a triple integral.
Do the triple integral, right? So if it says use the divergence theorem to find this area surface integral for a closed surface, if you calculate the surface integral, you never use the divergence theorem. Using the divergence theorem says, oh, I can calculate this instead, and by the divergence theorem, it's equal to the thing they asked for. Okay? All right, so I'm gonna look at one more example. Are we good on this one? So this is from Monday's homework, or Wednesday. It's Wednesday, the one I extended. Let's look at this. Compute the flux of the vector field, yada, 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 through S, which is the surface y equals x squared plus z squared within x squared plus z squared is less than or equal to 4. So let's draw that. So y equals x squared plus z squared looks like this. Right? This is 4. Oh no, that's not 4. Let's see. X squared plus z squared is less than or equal to 4. So this would be this is 4. So that y coordinate would be is it the other way around? These should be 2, and this should be 4. Yeah, so if x squared plus z squared is less or equal to 4, then y is less or equal to 4. So this is 4, and then it turns out that then the radius is 2. So if y equals 4, then our radius is 2. So this is 2 and minus 2. Okay. All right, so does this flux integral qualify for the divergence theorem? What kind of surface integral would you have to be doing for the divergence theorem? Closed, right? Is it closed?
No.
No, it's not closed. It's just this paraboloid, right? So we can't use a triple integral to solve this problem. Or can we? So what would the triple integral equal? So if I were to write triple integral over E of divergence of f dv, what would it equal? What surface integral?
The paraboloid minus the plus the disk. Sorry.
No, what surface integral would the triple integral equal to? What did you say in the end?
I said the surface integral of the disk plus the
Right.
paraboloid.
Right. So it'd be s for the disk, f dot ds, plus s for the paraboloid, f dot ds. Does everyone see that? So if to get the whole surface integral for that solid would be the two of these. And what's the problem asking for?
Just the one.
Just this, right?
Just minus the.
So we could use that divergence theorem by taking the triple integral and subtracting hopefully an easier surface integral, which would just be this vertical disk here. So let's do it quick. Make sure that, and then we're gonna put it in. We won't do it both ways. We'll just put it into WebWork and see if the answer is right. Okay. All right. So divergence of f is just negative x from the z component. Okay. And then we're gonna do what? Do r dy dr d theta, but then what is negative x in that? Yeah, this is a little screwy. I'll have to watch out. So it was negative r cosine. So the xz plane is this is a little weird. I don't know if we might get a sign wrong or something. But xz and y coming out this way. Yeah, it's cosine, but is it positive? Okay, we'll just go with it, and hopefully it'll work. But this is weird for polar and with y in the xz plane. Polar coordinates is a little screwy, right? Because if you did x cross z, then that'd be pointing in the negative y direction, right? See what I'm grappling with? Okay, anyway. So, and that's going to be, we do minus the surface integral of, so we need to parameterize that. We use, so it's a disk, so we use r and theta. ijk. So what is it going to be? R cosine theta, R sine theta. No. 4 R cosine theta, 4 R sine theta. Is that right? Okay, so then we're going to have r cross r, or the partial with respect to r is going to be cosine theta, 0 sine theta. With respect to theta, it's going to be minus r sine theta, 0 r cosine theta. So all we're going to have is a j component, and it's going to be, I got negative r. So I think we want to, so we got the order wrong, we want to make it positive, we're going to take the other cross product, and it'll be r. So then it'll be 0 r 0, right? So it's going to be y3 minus xz. Y is 4. 3 minus xz, but it's not going to matter because it's going to be dot r in the y component, so I'll just write it again, minus xz dot 0 r 0 dr d theta. So it's going to be 3r. And that's going to be from 0 to 2 and 0 to 2 pi of 3r. Okay, so then that's we're out of time. But that's the triple integral minus that's the surface integral. We're going to subtract out the surface integral for the disk, and that will leave the surface integral of the paraboloid, which is what they asked for in the problem. Unfortunately, I don't. What I'll do is I'll just stay and work it out. If you want to stay, you can, but you're dismissed if you need to slip out. So what is this? Minus r squared cosine theta times, and it'll be on the video. I'll leave the video running. Y goes from, oh, this is the triple. So 0 to 4.
Wait, but doesn't y go through r squared?
What's that?
Doesn't y go through r squared first? But not to 0.
Yes, yes. That's the thing I got on your case about. So it's going to go from r squared to 4, 0 to 2, 0 to 2 pi. So y is going to make this whole thing times 4 minus r squared. Is that right? Negative r squared cosine theta times 4 minus r squared. Okay, now with respect to r, I'm running out of room here. Okay, so triple integral, here we go. With respect to r, so is it negative 4/3 r cubed cosine theta? Please check my math. Plus, ick, r to the 5th, r to the 5 over 5 cosine theta? Is that right? And that from 0 to 2. So we're going to get 2 will give, what, 8, so negative 32 thirds cosine theta plus 32 fifths cosine theta. Check my math. And now we're doing d theta from 0 to 2 pi. Is everyone agreeing with what I got? Okay, and so then this is all going to just be sine theta, right? So it's going to be negative 32 thirds. Is it going to be 0? Plus 32 fifths. Everything's 0. So these flux integrals, these are equal and opposite. That's what this is saying, that the surface integrals are equal and opposite. So now we got to do the double integral. So that's the triple, this is the triple integral. Okay, and so now the double integral was this one that we found. Oh, that looks easy. So 3r squared over 2 from 0 to 2 is 6? 12 pi? And do we get positive 12 pi? But then we'd be subtracting 12 pi. And let's see if that makes sense. I don't know. So we think it's minus 12 pi? We think the answer is? Let's just try positive to see if we're in the ballpark. Okay, so somehow it's positive 12 pi. So I think that comes back to what I was talking about with doing polar coordinates on this disk right here. That there's an extra negative because of, it's kind of like, if you do cosine theta and sine theta, if x is r cosine theta and y is sine theta, that's actually opposite the right-hand rule. Do you see that? Because if you're going this way, that would indicate, by right-hand rule, would indicate this. So if you use x equals r cosine theta and y equals r sine theta, then you also need an opposite sign because the direction of positive y is in the opposite direction. So it would be minus, minus, and that's why you get the plus 12 pi. So for this, it probably would have been easier for this example to actually just do this surface integral, but we showed how the divergence theorem could be used this way.
Yeah.